Hello, welcome to all. I am Sachin Sambhaji Patil. I welcome to all of you for this session. So in this session we are going to see RC coupled amplifier, okay, then amplifier gain, voltage gain and remaining points. Once again I would like to welcome to all of you for this session. So as we know, in the RC coupled amplifier, this is common emitter transistor used here. Emitter terminal is common between input and output. So this is the RE resistor. This is the bypass capacitor is connected here at the emitter terminal. Okay, at the high frequency it will be on and low frequency it will be off. Okay, it is passing the high frequency component. Now in this common emitter transistor we can see this is the base terminal, collector terminal and this emitter terminal. So now at the base terminal we are using here R1 and R2 for biasing purpose of transistor. So biasing means this is acting as voltage divider. Okay, and it is giving the some voltage here. So this is connected to the R1 is connected to plus VCC and another end of R1 is connected to base of the transistor. So R2 terminal end is connected to ground and another end is connected to base of transistor. This is C1 is a coupling capacitor, okay, is using to couple AC input signal to the base of transistor. So as you know, C1 having the capacitive reactance XC1, so XC1 is equal to 1 upon 2 pi FC1. So 2 pi C1 is constant and frequency is variable. Okay, so capacitive reactance is inversely proportional to frequency of input signal. As frequency increases, the capacitive reactance C1 will be decrease. As frequency decreases, the capacitive reactance XC1 will be increase. So capacitor C1 is having XC1 is a capacitive reactance. So because of that, the C1 is passing high frequency component and it will be block low frequency component, that is a DC signal. So C1 is passing the high frequency component that is applied to the base of transistor, and R1 R2 is acting as voltage divider as a biasing resistors. Okay, then the collector terminal, there were connected the RC and another end of RC is connected to plus VCC. Okay, and here we are measuring the output voltage at collector terminal after coupling capacitor C2. Again, this is the coupling capacitor is passing the high frequency component and blocking the low frequency component. Okay, emitter resistor is here and bypass capacitor is here. So we can see this is the output amplified output voltage, but it is inverted. See here, this is the output voltage, it is amplified, means there is increasing the voltage level of output signal. Okay, and it is amplifying the input signal, and but we are getting the output voltage is in inverted form, means there is a 180 degree phase shift in the output voltage. Okay, so this is the amplified output signal and this is the AC input signal. So AC input signal is applied to the base of transistor. Okay, so input output waveform of common emitter amplifier. Here we can see the first figure shows input signal voltage Vi. So this is the y-axis is indicating voltage and x-axis is indicating time. So this is the input voltage is applied to the base of transistor. Okay, so in that case what is happening, so when we are applying the input voltage to the base of transistor, okay, this is the input voltage is applied to the base of transistor. So but as per this input voltage we are getting the here is base current, and as we know, this is the bipolar junction transistor, means the current conduction takes place due to the holes and electrons, and the collector current is beta times multiple of input current, that is a base current. So BJT is also called as current controlled device because output current, that is a collector current, output current, collector current is depends on input base current, and collector current is a beta times multiplication of input base current, means IC is equal to beta into IB. So beta is equal to IC upon IB. So beta is a current amplification factor in case of common emitter transistor. So output voltage we are getting here, that is having 180-degree phase shift with respect to input signal, but it is the amplified output voltage with 180-degree phase shift. So 180-degree phase shift between the input and output voltage. So output voltage is inverted version of input voltage. So VCC minus ICRC is equal to VCE. So this is according to voltage divider rule we are getting. So this is the VCC is the supply voltage, okay, and this is the voltage is given to here. So according to Kirchhoff's voltage law, the VCC minus voltage drop across resistor RC minus voltage drop across collector emitter terminal of transistor. So VCC minus ICRC minus VCE is equal to 0. So in that case, if we are assuming IC is equal to 0, if collector current is 0 put here, so we are getting VCC is equal to VCE. If you are assuming VCE, collector emitter voltage is 0, in that case then VCC is equal to ICRC and IC is equal to VCC upon RC. Okay, so we are getting selection of Q point. So as we know, this is the output characteristic of common emitter transistor. So in output characteristic, there is the x-axis is representing collector emitter voltage and y-axis is representing collector current IC in milliampere, and we are taking the observations or reading at a different parameters. First we are keeping IB, that is the base current is 0 microampere. In that case, if we are changing the collector emitter voltage, there will be change in the collector current like this. It is goes on increasing, it remains constant. The next case we are keeping base current IB is equal to 10 microampere and we are varying collector emitter voltage and we are measuring the collector current. So as for we are changing the collector emitter voltage, so there is a large change in collector emitter voltage, there is small change in collector current. Okay, so that is happening here. Next case we are doing IB is equal to 20 microampere, and by changing the collector emitter voltage we are getting the output response like this. So these are taking the different readings at different intervals, means we are keeping base current is a constant and we are taking for 0, 10, 20, 30, 40, 50 microampere. We are observing the when we are changing the collector emitter voltage, what is changing the collector current. When base current is a constant, we are keeping base current constant and we are changing the collector emitter voltage and we are measuring the collector current. So it is observed that the collector current is depends on input base current. So collector current is beta times multiplication of IB. So we can see this is the way getting actually how to draw this load line. So first of all we are assuming when collector current is 0, when IC is equal to 0, in that case VCE is equal to, that is a VCC. So what is VCC? 12 volt. Okay, we are seeing in this figure, you can see VCC is equal to 12 volt. What are we doing first? we are keeping base current is a constant, and we are changing the collector emitter voltage. Collector emitter voltage we are changing, and we are observing the change in collector current when base current is a constant. As base current is a constant, because we know that output impedance is very high, so that there is large change in collector emitter voltage, there is small change in collector current. Input impedance is low, so there is small change in VBE, base emitter voltage, there is a large change in base current. Okay, so that is happening. We are measuring the output characteristic, and what we are doing in the first case, we are applying this voltage divider, VC minus ICRC minus VC is equal to 0. We are keeping IC is equal to 0, then we are VC is equal to VCC, and when we are keeping VC is equal to 0, IC is equal to VCC upon RC. So we are finding the 2 points on the, this is the x-axis, VC is equal to VCC, when IC is equal to 0, and when VC is equal to 0, then we are getting, according to this, IC is equal to VCC upon RC. So we are getting this point, and by joining this 2 point, VC is equal to VCC and IC is equal to VCC upon RC, by connecting these 2 points, we are getting one line, and that line is called as DC load line. And we need to select the Q point. So Q point is operating point of transistor or quotient point of transistor. It should be present in the active region. This is saturation region, this is cutoff region, and this is the active region. So for proper amplification of input signal, the Q point should be present on center of DC load line, so the signal will be properly amplified. It should not be towards this, okay, it should be on center of DC load line. So when we are applying, so this is actually what is happening here. This is the collector current, and this is the actually shown base current. Okay, so when base current is changing from IB, that is a 40 microampere, 30 microampere, and 20 micro. Initially, what happens? Base current is changing from 30 microampere to 40 microampere. Okay, as when base current is changing from 30 to 40 microampere, there is Q point is shifting from Q point to R point, and when base current is changing from 40 microampere to 20 microampere, the base current that is the Q point is shifting from R point to S point. So what is your observation? When base current is changing from 0 to here, Q point is shifting from Q to R, and base current is changing from here 40 microampere to, that is the 20 microampere, that is the point is, operating point is shifting from R to S, again then S to Q. Okay, it is happening like this. So we can see this is in microampere and this is in milliampere. Means definitely this signal is amplified. Okay, so collector current is amplified. So IC is equal to beta times IB. So there is a 30 microampere or 40 microampere. Okay, multiply beta times, we are getting the collector current. Okay, so that is we can find the beta. Beta is equal to IC upon IB, 4 milliampere upon 40 microampere. By solving this, we can get beta. So that near about we are getting 4 into 10 raised to minus 3 and 40 into 10 to minus 6. Minus 6 goes up, it becomes minus 3 and 0.1. So 0.1 into 10 raised to, that is happening, plus 3. Okay, means we are getting beta. Okay, so beta near about 100 we are getting. Okay, you can check it. You can getting beta. So beta is equal to IC upon IB. So by solving this, we can get the answer. Okay. So selection of Q point. The key point should not be close to cutoff. Q point should not be saturation. It should be lies on center of DC load line for a proper amplification input signal, and output is exact replica of input signal. Okay. So thank you.